Donc on va commencer, je vais faire la présentation de Frédéric en français, puis il va prendre le relais en anglais après.
Ou en français, comme vous voulez, je sais pas.
Non, en anglais c'est bien, parce qu'on a des auditeurs qui ne maîtrisent pas parfaitement le français. Donc pour présenter Frédéric, il a fait sa thèse au LERMA, à côté, à l'Observatoire de Paris. Ensuite, tu as fait un post-doctorat pendant 1 an au CEA, puis tu as été recruté directement après cette année de post-doc. Et tu es toujours là-bas depuis. Donc, Frédéric, c'est un spécialiste simulation numérique sur les questions de formation de galaxies, en particulier pour ce qui est de morphologie, barres, disques, etc. Et aussi sur les problèmes de turbulence du milieu interstellaire, les galaxies à plus haut redshift et la façon dont s'organisent les nuages de gaz chaud dans ces galaxies au pic de formation d'étoiles. Voilà, c'est une thématique de recherche principale, je crois. Et Frédéric aussi le président du comité thématique 4 astrophysique géophysique pour le temps de calcul sur les calculateurs nationaux. Donc vous pouvez aller le taper après si vous n'arrivez pas à obtenir de temps de calcul, ou le féliciter. Voilà, je te laisse la parole.
Tu pensais pas si bien dire, Johan. Merci, Johan, and thanks everybody for the invitation. So my talk today will not be focused necessarily on my own work, so I can criticize more. But I want to address the question whether observed galaxies are a challenge for cosmological theories and cosmological simulations of galaxy formations. Because there have been many claims in the recent years that cosmological simulations on supercomputers of galaxy formation produce realistic galaxies. And basically, I will question this. So the question, the general problem is the following. Here's an image of a galaxy. I think this is the first known recorded image of a galaxy. This is an image of M51 drawn by Lord Rosse with his telescope 1850. We know basically the initial conditions of the universe from the cosmic microwave background. So the question is, can we explain the formation of modern galaxies, spiral galaxies, starting from these initial conditions, with our understanding of the universe, with our physical theories? So theories come with equations, but there are so many equations and they are so complex to integrate that you need supercomputers and you need simulation codes to put the equations in the supercomputers, and then you start from this, and you hope that the output will be this after a Hubble time, after the age of the universe. So the drawing here is nice, but let's look a bit more at what are the key features of galaxy populations in the nearby universe and in the distant universe for younger galaxies. So I will focus on galaxies that have roughly the mass of the Milky Way, which dominate in mass the universe, so 10 to the 10 to 10 to the 11 solar masses of stars. In the nearby universe, those galaxies are generally these galaxies with spiral arms, and you see on some examples that they have a bar, this elongated central feature. Even this one has a sort of oval distortion. And it's known since 20 years now, when you look at the near-infrared and you have a clear direct view of the stellar mass distribution, that virtually all galaxies today have a bar, or at least 90% of them. Pure spirals without bars are extremely rare. For more massive galaxies, this is the central elliptical of the Fornax cluster. More massive galaxies tend to be ellipticals. And an important fact for simulations that should be addressed is that the most massive ellipticals are what we call slow rotators, which means that even if they are flattened, the Fornax galaxy is a bit flat, the major axis is here, it's because the random motion of stars are not isotropic. This galaxy is flattened by anisotropic velocity dispersions, not by some residual rotation. It's clearly a non-rotating galaxy. It's a pure spheroid. So understanding galaxy formation means that we should be able to address this. So what about galaxies in the young universe? The main fact about galaxies in the universe is that they form stars more rapidly. The Milky Way is forming a few stars per year. When you look at galaxies at redshift 2, when the universe was 1/3 of its age, at the peak of the star formation history, a galaxy the mass of the Milky Way could form 100 solar masses of stars per year. They form stars much more rapidly. But there's a large consensus on the fact that they follow the same Kennicutt-Schmidt relation between the available gas reservoirs and the density of star formation per unit time. In blue, You have the low redshift galaxies. In red, you have the high redshift galaxies. No, it's the other way around. Blue is high redshift. So they form stars more rapidly, but this is just because they are more gas-rich. The conversion of a unit mass of gas into stars follows the same laws, the same processes. So young galaxies contain more stars, more gas. This explains their quicker star formation. And the gas, the depletion time, so the time scale to convert a unit mass of gas into stars is about the same for nearby galaxies and galaxies at redshift 2, 3, or 4. So there are very detailed observations now about the gas fraction of galaxies, of star-forming galaxies as a function of redshift. Still for Milky Way mass galaxies, it will be the same throughout my presentation. So this is the redshift, this is log of 1 plus z, this is the gas fraction for typical star-forming galaxies. So redshift 0, typically galaxies have 5% of gas, redshift 1, they have about 37, redshift 2 in this compilation, they have 52% of gas. So of course there is a large scatter. There are galaxies that have above the average or below the average. But the uncertainty on the mean value is very small. And the systematics also are very small because this has been done by observing CO, by observing C+, by observing dust, by comparing to the dynamical mass. Everything gives the same result. So the key point is that galaxies at redshift 2 have 50% of gas. There is a scatter about this, but the average value is 50. It cannot be 15 or 80. Okay? So that's for the global content of stars and gas of galaxies. So what's the consequences on morphologies? So this is like compilation by Delgado Serrano of the famous Hubble sequence of spiral disk and barred spirals at redshift 0, and these are images of galaxies at about redshift 0.7 that do not go in the Hubble sequence. They are very irregular. You don't see spiral arms, you see big blobs, big clumps that are clumps of star formation. And if you go higher in redshift, at about redshift 2, these are typical star-forming galaxies at redshift between 1 and 2, still for the mass of the Milky Way. You may have some spiral arms, but the images are dominated by giant clumps. Each clump can be 10 to the 9 solar masses of stars, so much more than a star cluster in the Milky Way. It's 1,000 times more massive than a star cluster in the Milky Way. So you have those clumpy irregular galaxies. Here are some other examples in the Hubble Udf. And this is not just because galaxies are far away that they appear like this, because if you take M81 at the same race frame wavelengths with the resolution and sensitivity of the Hubble Udf, here's what you'll see. You would see a spiral galaxy. So there's clearly something different at redshift 2 with galaxies that are irregular, clumpy. Probably the clumps form by gravitational instabilities. There have been many papers on this. Recently, the very existence of giant clumps has been questioned by 2 observations going to very high spatial resolution. There have been observations by Daniel Scherer's group using strong lensing to increase the effective spatial resolution, for instance, here in the cosmic snake, where they are saying, well, we don't see giant clumps anymore, we see 50 small clumps in the galaxy. And there have been very high resolution observations with ALMA mapping CO or dust at 100 parsec resolution, so 10 times higher in each direction than the HST, seeing smooth disk. So we've been wondering whether giant clumps really exist, but this has been addressed by the ongoing physics work of Baptiste 4 with me, using very high resolution simulations of high redshift galaxy, where he's showing that high redshift galaxies have giant clumps like this one or this one, but the clumps are not homogeneous. They contain many smaller star clusters. So if you go to very high resolution with ALMA or full lensing, you're not supposed to detect the giant clumps themselves. If you go to very high resolution and just run a clump finder, you will find one small cluster and another small cluster here and another one here and another one here, etc. This is for the ALMA resolution. Or if you go with lensing, this is a simulated galaxy, clumpy, like the typical redshift 2 galaxies observed by the HST. If you put a strong lens in the foreground and observe this galaxy again, you're not going to see the giant clumps. You're going to separate them into many small clusters, just like in the cosmic snake. So all the data are consistent with the very existence of gravitationally bound giant clumps. And this is nicely summarized by this picture from Murata et al. As a function of redshift, you have in a range the fraction of clumpy galaxies above 10 to the 10 solar masses of stars. And in gray, you have the fraction of weakly barred and strongly barred galaxies. So there is you can summarize the morphological evolution of galaxies with basically a transition at redshift about 0.7 between the early universe dominated by clumpy irregular galaxies and the modern universe dominated by barred spiral galaxies. So this is what cosmological simulations of galaxy formation should explain. At the same time, they should explain something else. They should explain the inefficiency of star formation and the quenching of star formation. We know that the star formation is inefficient because the ratio of the stellar mass of galaxies compared to the mass of their halos does not exceed 4%. The baryon fraction in the universe is about 16%. So only a small fraction of the gas has been converted into stars in galaxies, which is something that is hard to explain because if you think about the gravitational freefall time of gas into dark matter halos and the timescale of collapse into stars, you could convert 95% of the gas of the universe into stars within Hubble time if you don't have regulation processes. So you need something to regulate star formation. And there's also the famous bimodality of galaxy. This is a color magnitude diagram where there is a bimodality with blue galaxies that form stars and red galaxies that do not form stars anymore. So you need mechanisms to quench galaxies and regulate star formation, and there are basically two main mechanisms. One family of mechanisms is the halo quenching. This is a cosmological simulation with a galaxy here at the middle. It's surrounded by a halo of very hot gas, several millions of degrees, as large as the dark matter halo. If the gas is hot, it's maintained by thermal pressure. It doesn't accrete onto the galaxy and form stars in the galaxy. So halo quenching is one mechanism. The other mechanism, or series of mechanisms, is feedback, energy reinjection, either by young stellar populations, exerting radiation pressure, exploding as supernovae, or by AGN, supermassive black holes accreting mass. Here's a simulation with the gadget code of Volker Springel 15 years ago, two galaxies that merge. You have a central burst of star formation, feeding of the central supermassive black hole, and the energy reinjection blows the gas away and you end up with a quenched galaxy. So these are the two main series of mechanisms that you can use. So the challenge for cosmological simulations of galaxy formation, starting from the initial conditions of the universe, is to explain the diversity and the evolution of morphologies from clumpy irregular to barred spirals with inefficient star formation and quenching at the same time. That is, with galaxies that contain only a small fraction of the baryons of the universe. So, yes, Christophe.
You described the left-hand side mechanism as something which can be used. It's unavoidable, right? If you've got gas and you've got gravity.
It's unavoidable, but maybe it's not estimated correctly in the cosmological simulations. It's unavoidable in some sense, unless you have an extremely poor. Well, if you do a simulation with a resolution element as large as the dark matter halo, you will avoid this. And then you will need feedback. So these are the two features that you want to explain. Quenching inefficient star formation, morphological evolution. So do cosmological simulations reproduce this correctly? Do we understand galaxy formation? Apparently the answer is yes. This is a press release from the Eagle simulation 2015. So we have understood galaxy formation. They are stunningly realistic galaxies in cosmological simulation, so we can do something else like planet formation or anything you like. So stunningly, une nouvelle simulation de l'univers produit des galaxies incroyablement réalistes. Incroyablement ou incredibly, it's even stronger. Okay. Here's another one with illustrates TNG, which is a series of simulations by Volker Springel, Larsen Swiss groups, released over the last 2 years. So the simulation offers a glimpse of what our Milky Way was when the Earth formed. The Earth formed at redshift 0.7. So the morphology should start to be different. No barred galaxies, clumpy galaxies. We will check this. Another one said, we can accurately predict the influence of supermassive black holes on the distribution of gas on cosmic scales. With all due respect to Volker, we will check whether this is accurate or not. And the third member in the press release said, this is more honest. This is maybe why we need women in science. Our predictions can now be systematically checked by observers. So I have summarized the observations, so now let's check the predictions. So there are actually many cosmological simulations of galaxy formations. There are two main types. There are the zoom simulations. You simulate a big piece of the universe with a low resolution, and you increase the resolution on one target galaxy. And you do another simulation with a zoom on another galaxy, one by one. The other strategy is the large volume simulations, like illustrates. You do one single simulation with the high resolution on all your galaxies, and in one simulation you produce many galaxies. So I will focus on the two most cited simulations of galaxies formation. One is a series of zoom, fire simulation. The other one is the Illustris series of simulation. They use different simulation code. One is using a sort of modified SPH where you have points that get close to each other when the density is high and far from each other when the density is low. In Illustris with the ARIPO code, you have a moving mesh, but it's the same idea. You have some particles or some points, and if the density is low, they go far away, so the cells, like the green cells, will get larger. And if when the density is high, the points get closer to each other, so you increase the resolution. So your resolution naturally follows the density, which sounds good. So before I criticize a little bit, I want to emphasize that those simulations have correct star formation histories, star formation efficiencies, stellar masses at any redshift. So the inefficiency of star formation and the quenching of galaxies are nicely reproduced by those simulations. And it's strongly emphasized in the papers. Let's look at the morphologies. These are morphologies of the fire to galaxies from a paper last year. I don't see any bar, but these are redshift 0 galaxies. Is there any galaxy in the universe that doesn't have any bar like this one? François says no. Maybe there's one, but they have many. It's the same in the Illustris simulation. These are redshift 0 disk galaxy. There is one bar here, there's one weak bar here. 90% of their galaxies do not have a bar. So where are the bars? The bars are in ellipticals. These are red, non-star-forming quenched galaxies, which at least some of them should be pure spheroids, slow rotators flattened by anisotropic dispersion, no rotation. If there's no rotation, you cannot have a bar. The bar is an instability in a rotating disk. They all have bars. So you have the bars, but not at the right place. And actually, it's because the ellipticals are too disky and too rotating, and there's a nice paper by Mark Huerta's company this year showing this. You can find the bars somewhere else. This is the redshift evolution of some galaxies. No bar at redshift 0. There's a bar here, there's one here, there's maybe one here, there's one here, there's one here, there's one here, there's one here. So you should have bars in low redshift disk. You don't, or almost. You shouldn't have bars here and there. So you have bars, but not at the correct place, and you don't have clumpy galaxies at a redshift. You have nice barred spiral galaxies at redshift 2. And it's the same in the fire simulations. And they wrote papers saying, no, there are no clumpy galaxies at a redshift. Look here, we have a spiral galaxy. Well, a giant clump is forming, but within 10 million years, it's disrupted. So giant clumps are very rare. I'm focusing on two simulations because they are the most recent and most cited. This is true in almost all cosmological simulations, except a few ones that I will detail later. Okay? Well, for instance, IRIS, the world's first realistic simulation of the formation of the Milky Way, I don't see a bar. Even Lord Ross, 1850, knew that M51 has a weak bar. He has drawn the bar. You don't need the ELT to test simulations. So, why do cosmological simulations fail to reproduce realistic galaxy morphologies? That's the interesting question. I see four plausible explanations. It's a matter of numerical code resolution. Dark matter is wrong. The dark matter halos around galaxies. Cosmology at larger scale is wrong. Or they just don't deal with the baryonic physics correctly. So let's try. First hypothesis. problem of code, of resolution. Well, this is a simulation by Conde and Sanders, 1981, with the incredible resolution of 32 times 32 times 16 cells. Incredible at that time, but, well, that's enough to get a bar. So if you model an entire galaxy with this means your resolution is 1 kiloparsec. The resolution of Illustris TNG is 100 parsec. So it's not a question of resolution. Is it a question of code? Well, it's pure n-body, no hydrodynamic.
Is there dark matter in this simulation? There was dark matter in this simulation in 1981.
Is there a dark matter halo? No, because it's a flat box, but you can take Combe-Gérin 85, there is a dark matter halo and they do get a bar. They have no hydrodynamics, pure hydro. So it's not a question of whether it's SPH, AMR, RAMSIS, ARIPO, which code. You cannot do a worse hydro code than no hydro. So it's easy to get a bar. So those simulations should have a bar. Other hypothesis, the dark matter halo properties are wrong in the cosmological simulations. That's why they don't form the bar. I don't think it's the case because, if anything, the problem of cosmological simulations in forming dark matter halos is that they form dark matter halos that are too cuspy, too concentrated. And this should help to have barred galaxies because this will help to form a bar. Because when you have a seed bar, it will undergo dynamical friction on the dark matter halo. This is exactly what you want to form a bar. You want to remove angular momentum by dynamical friction. And also because bars may destroy themselves by gravity torques, but the spherical dark matter halo will dilute the gravity torques, and this will promote the bar. And Françoise has shown this nicely, that this is the same galaxy in a dark matter halo with a core and with a cusp. If there's a cusp, you promote the bar. So cosmological simulation, if they are too cuspy, they should overestimate the bar fraction. Is cosmology at large scale wrong? We have done simulations with Katarina Kraljic, Marie Martig, where we model we simulate galaxy-sized boxes, just one dark matter halo with one galaxy, but the merger history and the diffuse accretion history are recorded in a large volume cosmological simulation. So we have all the cosmological history, and the Orion shows the bar fraction as a function of redshift. The gray and the green points show the data from Cosmos and candles. We get the bar fraction correctly with the lambda CDM accretion and merger history. So maybe it's the fourth hypothesis. Baryonic physics is wrong. And this might well be the case because, remember, redshift 0 galaxies have typically 5% of gas. People like Liat and Asula have modeled hundreds of galaxies with 5–10% of gas. They always form a bar. I'm showing 3 ones. I mean, even a more or less realistic galaxy, if you don't want to form a bar with 5% of gas, well, if you put the mass of the Magellanic Cloud in the size of the Andromeda galaxy, which is crazy, maybe you will not form a bar. But if you do something that's not crazy, you end up with a bar. It's the same at redshift. At redshift 2 with 50% of gas, take any simulation code at any resolution for any realistic setup of a galaxy with 50% of gas, as was done by Noguchi in the last century, it will break up into a few giant clumps. So maybe the gas fraction is not correct in the cosmological simulation. So let's have a look at this. Fire first. Oh, sorry, the redshift is not written. It's redshift 3 here, redshift 2 here. So redshift 2, 20% of gas. This is counting all the gas in a 25 kiloparsec radius. So not just the gas in the galaxy as observers do. So it's sort of overestimating. More recently, so massive fire. So redshift 2, we want the circles for star-forming galaxies in blue. Okay, there's one here at 30% of gas, because this is gas over stars. The other ones, most circles are here. 20% for gas over stars, so gas over baryons is 15%. 15, not 50. But you have to dig in the appendix of the papers to find this. The Illustris simulations, so Illustris TNG, well, let's look. Redshift 2, mass of 10.5 to 11, the gas fraction is 15%, but it should be 50. Does it explain the mismatch of morphologies between real galaxies and cosmological simulations? I think so. I have re-simulated the galaxies from fire with exactly the same rotation curve, dark matter halo mass, stellar mass, gas mass. So with their 15, well, it's between 15 and 20 gas fraction, with Ramses, with a very high resolution, with my preferred cooling and feedback recipes, here's what I get. I agree with them, with this gas fraction. There's no giant clump. Oh, there's one here forming in a spiral arm, but rapidly sheared away. It's a spiral galaxy. Just like they said, okay, you may have a giant clump, but it's very rapidly destroyed. Like, there's 3 million years between the images. So in the spiral arm, there's a clump forming here, here. It has disappeared. There's one forming here. You see it here. It's been sheared away. Because the galaxy doesn't globally produce giant clumps. Only in spiral arms you increase the density, the gas gets unstable and fragments into clumps, but the spiral arms are location of radial compression, and the Coriolis force will just convert the compression flow, the radial compression flow, into a shear flow, so you disrupt the clumps. Even without feedback, it's not feedback. So I've done the experiment of simulating the same galaxy with the same rotation curve, the same dark matter halo, the same total mass. I just change the gas fraction. I replace stars with gas to get a 50% gas fraction. And here's the result. Oh, it's a clumpy galaxy. It's not a barred spiral anymore. And this is really the gas fraction that dominates, because I have artificially, in the low gas fraction case, reduced the feedback to make sure it was not feedback disrupting the clumps. And I have artificially increased the feedback in the high gas fraction case. Spiral, clumpy, irregular. So it's not feedback, the problem. It's the gas fraction. So cosmological simulation typically lack clumpy galaxies because they have too low gas fraction in the young universe. And it's the same for bars. The series of simulation by Martig and Kraljic I was showing have high gas fraction at redshift 2, maybe a bit too high, and lower at low redshift, maybe a bit too low at redshift 1, but they have high gas fraction and then lower gas fraction. At redshift 1, they have clumpy irregular galaxies, barred galaxies at redshift 0, with the transition about redshift between 0.5 and 1. So I think all this is caused by the gas fraction. But then why do cosmological simulation produce galaxies that like gas? It's not because the gas doesn't fall off galaxies. It's because they expulse the gas from galaxies very efficiently through feedback. The energy reinjection, the momentum reinjection from young stars, supernovae, black holes, AGN, produces very efficient galactic winds. This is in the illustrated simulation. You have a galaxy, the disk is perpendicular, it is vertical here. So that's temperature velocity. So the galaxy is here, and you see this very high velocity, 2,000 kilometers per second ejection of gas. So the key parameter for this is what people call the loading factor eta. It's the outflow rate of gas, so that's the mass of gas removed per unit time in the galactic winds, compared to the mass of gas converted into stars in the galaxy. So what is it in the illustrated simulation? In illustrated TNG, there's a very recent paper by Nelson and collaborators. Well, for very, very massive galaxies above 10 to the 11, it's low at high redshift, and then it's increasing below redshift 2. But for all galaxy masses below redshift 2, it's between 1 and, 1, it's the log. It's between 10 and 30. 10 to 30. So you inject 20 times more gas than you turn into stars in the galaxy. It's the same in fire. Fire simulations, mass outflow rate, 10, 20, yeah. And it's the same in many other cosmological simulations. Is this realistic? Well, let's look at the data. There are two ways to probe the outflow rate from galaxy. One way is that when you have a galaxy accreting gas in some direction and expulsing gas in an outflow, is to look at background quasars close to the galaxy, but a bit offset from the galaxy. And in front of the background quasar, you will have absorption that will probe the outflow density and velocity, and you will turn into an outflow rate. The group of Nicolas Boucher in Lyon is doing this, and this is the result of their mega flow survey on Muse. Many galaxies with different, well, this is tracing the galaxy mass. It doesn't depend much on galaxy mass. It ranges, it's between 0.1 and 10. The median value is about 1, about unity. Oh, and by the way, so there are some analytic models. Many of the lines are analytic models. The dashed black line here, Hopkins, is the fire simulations. You see it's above. The green line here, Fokelsberger, this is the illustrated physics. Wow, it's 10 times more efficient. There is another way to probe outflows. which is to look directly at galactic disk, produce their spectra, and see that when you look at, for instance, the H alpha line, there is a narrow component with a dispersion of a few tens of kilometers per second, which is gravitationally bound to the galaxy. That's the ISF of the galaxy. And there is a broad component with a velocity dispersion of 100, 200, 300 kilometers per second, which is, with this velocity, it can only fly out of the galaxy, so that's the outflow. And with CHEMOS, the MPE group has some statistics on the loading factors, which are between 0.1 and 0.3. So they are below those obtained by background quasars. But we have an explanation for this, which is that the outflows are variable in time. A galaxy will tend to expel shells of material. And if a galaxy expels a dense shell at some time, it's there, but later on it's there in green, and later on it's there in red. With a background quasar, you will always be sensitive to the dense shell, so the maximum, the peak of the outflow activity, until the shell disperses in the IGM beyond the virial radius. Well, here's an example of a simulation of a star-forming galaxy. The disk is synergion. And oh, yeah, there's an outflow phase here, and there's one here, and there's another one. There's another one, and it will end up with an even more efficient one. So you see it's very variable in time, and then the background quasar technique will be sensitive typically to the maximal outflow rate over the last 100 million years. So it's not sensitive to the average accretion rate. We've done a large series with the 3D gas flow ANR team led by Nicolas Boucher. We've done a large series of simulation of this and have some statistics, and we find that this is probing the maximal outflow rate average over 10 million years during the last 100 million years. It's overestimating the average by a factor 3. So if we combine both techniques, we have an explanation between the outflow rate, the mass loading factor, which was about 1 on average with background QSOs, and closer to 0.3 here. In any case, it's probably lower than 1 on average. It's clearly not more than 1. It's not a factor 10 or 20 like in all those cosmological simulations. So if I summarize what I've told so far, the most recent and detailed cosmological simulations of galaxy formation tend to fail to explain morphologies. They do not produce barred spirals at redshift 0, or very few of them. They should dominate. They don't produce clumpy disks at high redshift. They don't produce pure spheroids, non-rotating ellipticals, even for very massive CD galaxies. We know that the gas fraction in those simulations is clearly too low, especially at the peak of star formation, which is at redshift 2. And there is a direct link between both. It's because they lack gas that they do not explain clumpy disk. It's because they are too gas poor at high redshift that they form bars at redshift 2, and then those bars dissolve by redshift 0. And we know that they lack gas because of excessive galactic winds that are a factor 10, maybe a factor 50 above what's observed. But I don't want to be too critical because they don't have a better solution. If they don't have this very efficient expulsive feedback, removing gas from galaxies, they have too efficient star formation. All the baryons, all the gas will fall in galaxy, convert into dense gas, and convert into stars. The Milky Way will be 10 times more massive than what it should be. The global stellar content of the universe will be way too high. And there wouldn't be galaxy quenching, or very few galaxies would be quenched. So there's a good reason to use this very efficient feedback. But this means you cannot have the inefficient star formation and quenched galaxies along with correct morphologies. So there's a conflict between both. Just to come back to this, the moral of the story so far is that if you want to do precision cosmology, it might not be a good idea to use a simulation that reinjects 10 times too much gas from galaxies into the IGM. Because what you observe with Lyman alpha forest or Euclid, it's the baryons that you observe. So you need to know where the baryons are accurately. Now, there is at least one simulation that is doing better. No one paid me for this talk. No one paid me for this talk, and actually I think the Horizon AGN team does not sufficiently advertise this, because if you want to know what the gas fraction of typical galaxies at redshift 2 in Horizon AGN is, you can find it only in the appendix of Velker et al. 2017 paper. You can find it, but it's only in the appendix. Well, tell me if I missed something else. So for galaxies above 10 to the 10, so massive galaxies, redshift 2, they have 53% of gas. Exactly the value compiled by Tacconi et al. Last year. Is it because the outflows are more realistic, that maybe they do not eject too much gas from galaxies? So I asked Ricarda Beckman, who unfortunately is not here today, to give me the loading factors in Horizon AGN. So this is redshift 2. Maybe you cannot read it. This is 10 to the minus 1, 10 to the 0, 10 to the 1. Okay, so the loading factor is 70%. It's about unity or a bit below. So the mass that you remove from galaxies in winds is comparable to the mass that you convert into stars in galaxies. Remember, in Illustris, it's 20, 30. That's a huge discrepancy. And that redshift, so that's redshift 2, redshift 0, the value is about 2, so it's about unity, slightly increasing with redshift. This is what's observed. And then you get the correct gas fraction. And then you get the correct gas fraction, you get the correct morphologies. These are redshift 0 galaxies in Horizon AGN. You have strong bars. These are redshift 2 galaxies in Horizon AGN. This is very irregular. There are some blue clumps here, and if you were observing with the HST, because of the band shifting at high redshift, you are sensitive to the blue emission. So you would see a few blue clumps here again. Maybe it's not as clumpy as real galaxies, but this is closer to high redshift galaxies than what I've shown before in other simulations. But this makes sense because the gas fraction is correct. And I told you, if you have 50% of gas in a galaxy, it's not going to form a bar, it's going to form clumps. It's maybe not the only one. So Horizon AGN is a large volume simulation, homogeneous resolution strategy. There is a series of zoom simulation where you have a large volume and you zoom on one galaxy, then another one, like Fire, which is called Vela. So it's performed by Daniel Severino and collaborators. It's used by Decal's group. The loading factor of outflows is on average 1. And the gas fraction here as a function of SSFR, who cares? Gas fraction at redshift 2, so we want the green-blue points. Here, 40%. Maybe not 50, but not bad. At redshift 4, 60, 70%. Much more realistic than other simulations. This is done with the ART code. And something surprising is that those two simulations, Horizon AGN and the Vela series, use adaptive mesh refinement codes. Like you know, because this is the case of Ramses, which was written in France by Romain Tessier. So everybody knows Ramses. This is the grid, the adaptive mesh grid of Ramses around the galaxy cluster. Well, basically resolution follows the density, just like in those other codes. There's still a resolution, a difference, which is that with adaptive mesh refinement, you have a minimal resolution level, which is the grid in yellow here, and you cannot drop below that resolution. With the other codes, if your particles or your points go far away because the density decreases, the resolution will continue and continue to decrease. Here, the resolution follows the density, but there's a minimal resolution that you control. I did not expect this to be important until with a student of my group, Solène Chabanier, we did the experiment of redoing the Horizon AGN simulation with a resolution improved by a factor 2 at the coarse level, which means basically on such a grid, this would mean that all the yellow cells you split in 2 cells on each axis, so 8 cells in 3D. You increase the resolution where it was low. You don't change the resolution anywhere else. So you only increase the resolution in the low density intergalactic medium. And this is the ratio of the power spectrum before and after this experiment for the Lyman alpha forest gas, so basically the neutral hydrogen gas on large scales. You have differences between 10 and 20%. But the neutral hydrogen that is not in the IGM has to be somewhere else, like in galaxies or in the hot halos of clusters. So maybe this has an impact on galaxy formation, actually the detailed physics of the IGM. So we wanted to probe this further. So what we are doing currently is that we are running the extreme horizon simulation. This is a grand challenge simulation we are doing with Solène, with Johan Dubois, Christophe Pichon, and many others, on the new partition of the Joliot-Curie supercomputers at TGCC with the new AMD processors. So it's using a large number of processors. So the box is 50 megaparsec, so it's a smaller box than Horizon AGN, but we have a very aggressive refinement strategy. So the low resolution in diffuse gas in Horizon AGN was 100 kiloparsec. We have everything at 50 kiloparsec, but we have almost everything at 25. 93% of the mass is at least resolved 4 times better on each axis in 3D than in Horizon AGN. And what used to be at 50 kiloparsec in Horizon AGN is now at 25 or even, sorry, it's 12, etc. But we don't change the resolution in galaxies. When the resolution is 1 or 2 kiloparsec, we keep it the same. So we have the same physics in galaxies, we have the same star formation recipes, we have the same supernovae feedback, AGN feedback, etc. The simulation is running currently, so all this is very preliminary. But here's a temperature map of extreme horizon at redshift 3. So you have a protocluster, you have a void, you have filaments. So if you cannot read, basically 1 million degrees in red, this is 10 to the 5, this is 10 to the 4. This is the same resolution, the same simulation, the same box at the same redshift with the Horizon AGN resolution. Wow. The mass of gas above 1 million degrees is 3 times larger here than here. This galaxy here is in a hot gas halo, so it's potentially quenched. The same galaxy here is in a cold filament. So you see, Christophe, that the hot halo quenching is unavoidable, but if you lack resolution, you may be able to avoid it. This galaxy here has produced a large hot halo quenching its satellites. It's a small halo here. What else? This one here barely has a halos. The halos here of several protocluster regions have percolated. Oh, there's a protocluster here that has a very large halo quenching, well, at least cutting the supply in fresh gas from all galaxies in this volume, not here. Let's zoom on this region. This is this hot bubble from the very massive galaxy here. The highest temperature is here because there's a shock propagating, it's a shock. All the small points you see are the cold points in yellow are cold spots, they are galaxies surrounded by gas at several million degrees, so the supply of fresh gas to grow those galaxies has been cut, so they are virtually quenched before redshift 3. Here, the same galaxies are in cold filaments calmly accreting gas. So they can continue to grow, form stars, etc. Feedback is no different. We have the same star formation recipes, we form the same stellar mass, we have the same this is the black hole mass versus stellar mass, so we have the same Magorian relation, it's all similar. And I've been zooming on an example, but you can see that it's something systematic, and again, the mass of gas above 1 million degrees is 3 times higher here than here. This is something I produced last night. Well, the simulation is running. So don't ask me the explanation, but I know it's not feedback. Feedback is not different. So it can be shocks. There are shocks that are better resolved. It can be because at low resolution in the IGM, you overcool the gas because the cooling rate at the average density is very different from the average of the cooling rate. It can be metal redistribution for cooling that is different. I don't really know. But what's very important to keep in mind is that this is still the resolution of Horizon AGN with an AMR code that has a minimal resolution level. With most numerical simulation codes, in particular in Fire or Illustris, the resolution in the IGM can be much worse than this. So we are continuing the series of simulation, but probably if I was showing the Illustris-like resolution, or even worse, the Fire-like resolution, because Fire is zooming on one galaxy, but outside of the zoom region, the resolution in the IGM can be 500 kiloparsec. Here it's 100, here it's 25. In Fire, it can be 500. So it would probably be worse. So this is a tentative conclusion, because this is new. But it seems that we are finding that resolution in the large-scale diffuse intergalactic medium, circumgalactic medium, CGM, not ISM, is important. It changes the story of halo quenching. And many galaxy formation simulations have focused on having high resolution inside galaxies, which is nice. But if you don't have the high resolution around galaxies, you're going to underestimate the halo quenching, which is unavoidable but might not be estimated correctly. And then to quench your galaxies and regulate star formation, you'll have to boost the energetic feedback mechanisms. You're going to deplete your galaxies from gas, and you're not going to have the correct gas fraction histories, star formation histories, and morphological histories. And coming to this again, if you want to do precision cosmology, you need a simulation that accurately predicts the row distribution of baryons between galaxies and the AGN. And frankly, the best simulation I know to date is Horizon AGN. So here's a view of the extreme Horizon simulation, just a portion of the box where you have hot gas halos. The dark spots in the hot halos are galaxies about the mass of the Milky Way that are quenched, at least some of them, earlier in this new simulation. They quench at redshift 4 rather than quenching between redshift 1 or 2. So I think it's time, so I will end up here. Yeah.
Merci pour cette présentation. Pour le chèque, on s'arrangera après. Les questions?
It was beautiful talk. Well, I have some questions, a lot of questions, in fact. In fact, you said that bars were forming at z=2 in the low resolution in voids simulation like Phi or Illustrates. But why do the bar don't last long? Do you think that the gas is destroying the bars or not? And why also the ellipticals are not ellipticals due to the merger and so on? So why you find so much disky ellipticals and so on?
Okay, so why do they form bars? Why do the bars disappear? And why there are bars here? So why do they form bars? They lack halo quenching, presumably, tentatively. That's my proposal. They lack halo quenching in those simulations because they don't resolve correctly the varial shocks, etc. So they rely on expulsive feedback. So the gas fraction here is 10–20%. And as you know, if you run a simulation with 15% of gas and with something more or less realistic for the galaxy mass and size, you will get a bar all the time. Then the bar has disappeared here. So it might be the effect of some mergers, but I think it's mostly the gradual effect of angular momentum exchange with the gas. You and I have shown that within 10 billion years, if you don't accrete gas again later on, you will destroy the bar.
There's not enough gas for that because you have this, not enough gas for that.
Yes.
So the stellar bars should at some points...
now, why do you have a bar here? You have a bar here because those red early type galaxies are not pure spheroids. They are S0s, actually. They are all lenticular galaxies, so they are thick rotating disks. Why? Because I think, again, this can be explained by the lack of halo quenching. If you had really a very hot halo with a nicely resolved virial shock, there would be no accretion at all on those galaxies. And if you have one or two big mergers, you will turn a pure disk into a pure spheroid. I think the lack of resolution at the virial radius or beyond the virial radius is such that those galaxies do accrete some gas, continue to expel gas through feedback. They are not totally quenched. And as soon as you accrete some gas, you have some rotation, and if you have some rotation, you can form a bar.
Yes, but
Mark has looked at the morphology, and it would be interesting to look at the angular momentum. I think there's too much angular momentum in those galaxies.
But what you say for ellipticals could work for spirals. They are not quenched, so they are continuing accreting gas and forming bars.
So yes, you're right. So there's probably something worse, which is that the mass distribution of those disks is probably not correct. Because if the mass distribution was correct, they would reform a bar. So it's even worse. No, but that's true. The fact that they don't display a bar on the 2D images means that the 1D radial profile of baryons is not correct.
So thank you for the nice talk. Could one of the reasons for the excessive loading be lack of resolution? I mean, realistically, you might punch holes in the gas and so much of the energy might then escape without actually dragging so much gas with it?
Could the low resolution? Yes, but could be, because with a higher resolution you would have at least some pieces of gas that would get denser, and some would be lower density. And actually, if you have an heterogeneous medium, on average you cool faster. If you have a gas that is low density everywhere, basically the cooling time is very long. If there's one underdensity and one overdensity, the underdensity doesn't cool, but that's the same thing. The overdensity will cool. So probably with the lack of resolution outside of galaxy, you may store the energy. You may overestimate the energy that outflows keep. This might be a part of the explanation for our new result.
Thank you. A very nice talk. Thank you, Frédéric.
Thank you.
I think it is essential to analyze the galaxies at redshift 0 and redshift 2. But to say that redshift 2 galaxies are primordial, I don't agree with that, okay? Because we are discovering a lot of galaxies at redshift 3, 4, and now 8 and 10. In that case, the morphology is completely unuseful. Why? Because you have the fading effect. And we are staying with a star formation history to decide. And the star formation history is possible from stars. And I am very surprised because in these models, there is no star models. We analyze in Pegasus and so on, or other models, the properties of stars, the calibration of the photometry from the luminosity of stars. So what is the future? That is an expert. You are an expert. What is the future of this experiment from galaxy population at redshift 8?
Go for it. So let me take it easy and go back to the beginning of your comment. Galaxies at redshift 2 look like this, not like nearby spirals. Are they primordial? Maybe not. Maybe I shouldn't say they are primordial, because it doesn't mean that galaxies above redshift 2 at any redshift are like this. Maybe they are not born like this.
Sorry, they are active, of course. I find that
Yes.
but that this activity is not a primordial activity. You understand?
Yes, yes. But they have this morphology, so any model should account for this. Then redshift 8, they can be different in terms of morphology and star formation activity. I don't think we have large enough statistics about galaxies above redshift 5 to really constrain cosmological simulations. Right now, in a few years, yes, of course, there will be another line of constraints at higher redshift. Before being like this, they are different. And we will have to explain this as well. I agree. But,
Just a small question. What about the giant clumps? You mentioned the giant clumps.
yes. So the clumps that we see everywhere in those galaxies. I would assume that they are at redshift 2 and not at redshift 0 because you need high gas fractions. At low redshift, below redshift 1, you don't have enough gas to form the giant clumps. But I also think that to form giant clumps, you need dense enough galaxies because it's a gravitational instability. So I would expect galaxies at redshift 5 to be very gas-rich, but low mass, low density galaxies that probably don't have this kind of giant clumps. That's just my bet. But I expect galaxies at redshift 5 to be non-clumpy. Maybe irregular through streams, but not through clumps, gravitational instabilities. And if true, observations will tell us, but if this is true, this will need to be explained by cosmological simulations as well.
the new simulation with the hot halos, with the halo quenching. versus the classical feedback quenching of high redshift galaxies?
Well, it's not versus, it's in different proportions.
Yeah, in different proportions. So if I was to go out and observe some massive redshift 2 to 4 quenched galaxies, what observational signature would I look for to try to distinguish what killed the galaxy? I mean, whether it was a hot halo or an AGN.
I have no answer. The data for this were produced 48 hours ago. No, well, might be like, I don't know, clustering position with respect to protoclusters. Like here, you will have many galaxies that might be quenched because they are in the very large hot halo of a few very massive galaxies. And the same galaxies in this region are not quenched because they are not in the hot halo. So it can be the position with respect to the large-scale structure of the skeleton. Just a guess. I don't have any robust analysis. All I can say is that changing the resolution in the AGM changes the amount of hot halo quenching by large factors.
Yeah, you were mentioning that the simulations can reproduce correctly the star formation histories in galaxies. So I was wondering at redshift 2 for these galaxies with high gas fractions and clumpy galaxies, how do you know that you are reproducing correctly star formation histories?
Okay, so the star formation rates are correct. The star formation efficiencies are not. Because they have the correct star formation rate. For instance, in the fire simulations, integrated over the whole galaxy population. It matches the star formation rate of the universe per unit volume. But they don't have the correct gas fraction. So if they don't have the correct gas fraction, the efficiency, which is star formation rate per unit gas mass, cannot be correct. It has to be too high. But it's, well, I didn't display the plots, but if for the fire simulation, look at Phil Hopkins' paper, so 2015 A, B, C, D, etc. It's easy to find. It's in all the papers. The gas fraction, it's in the appendix on one paper.
Yeah, we're probably talking about different definitions of star formation histories then.
If your definition is star formation rate as a function of time, integrated over the mass function of galaxies, so you take 50 megaparsec co-moving in the universe, their SFR as a function of t matches observations. Well, there might be a factor 2 or 3 discrepancy. So there is actually the...
It's distributed differently within the galaxy.
You mean the spatial distribution?
Yeah, fine, but so why do you say that is right?
No, I'm saying even in observations where I've had a hard time to get star formation history.
Okay, so there is some... The agreement is within the uncertainty of the observation, which is maybe a factor 3 or 5. And maybe within the range of observations, they are at the bottom or at the top, but it's not a factor 30. When you look at outflow rates, remember the loading factor is in Illustris is between 10 and 30 for star-forming galaxies. In observations, it's below 1. So the discrepancy is a factor 50. You don't have a factor 50 for the star formation rate as a function of time. I agree, it's probably not fully correct. I'm not sure I have my backup slide on this. Let me... let me show you something. No, it's not this one. Okay. So, star formation rate density from observations, I don't remember the reference. One set of observation here, the points. And in the Illustris simulation, you see that Illustris is clearly above at low redshift. Okay, but the discrepancy is not a factor 50. That's what I meant. There's some disagreement. Stellar mass function of galaxy. The observation are in the points. The Illustris is a dashed line. Illustris is above for low mass galaxies and high mass galaxies. Factor 2 or 3. So they are not fully realistic, but they are probably more realistic on this aspect than on the question of morphologies, gas fraction, outflow rates. I hope this answers your point. I agree it's not fully realistic. The star formation rate as a function of time cannot be fully realistic if the gas fraction is not realistic.
Shifted the population.
Yeah.
So, Frédéric, a beautiful talk. I enjoyed it very much.
Merci, Gary.
I think there's still a lot of things that we fail to understand. I was very impressed by a thesis I heard in Marseille by Arturo Núñez, who did a thesis with Emmanuel Nesri, where he ran Ramses simulations, zoomed Ramses simulations to reproduce Milky Way-like galaxies with two different recipes, or several different recipes for star formation and several different recipes for supernova feedback. And the morphologies of his galaxies at redshift 0 were very different. Mm. So I was amazed. I mean, some of them were very clumpy, abnormally clumpy, and I was surprised that none of them had bars. And also, as you mentioned, his dark matter was too cuspy. Okay, it was cuspier than NFW. So that's one comment I wanted to make. So I think it's very difficult we still haven't understood the recipes we need to put in the hydrodynamical simulations for star formation, for supernova feedback, and the worst, as you mentioned, for AGN feedback, which is the most difficult.
The simulations you refer to are cosmological.
They're cosmological zoom.
Zoom in. Yeah. There's something really, just to react on this point, thanks for the comment, and something really striking is that there have been many cosmological zoom-in simulations with, as you see, changing the recipes for star formation, like the efficiency, the threshold, the clumpiness of star formation, whether it's density-based, based on local virial criteria, the feedback, the cooling of gas, metals. It's very hard to produce a bar. Now, when you do an idealized simulation of a galaxy, unless you take something crazy like the mass of the small Magellanic Cloud in the size of Andromeda, you always get a bar. Look at all the papers of idealized simulation of disk by Françoise, by Lea Tanasula, by Daniel Feniger, by all those people. You will never find a galaxy that remains unbarred. That's striking. I agree. I don't know why.
Well, because their simulations were isolated, so maybe if you have a infall of minor mergers and all that, that might bring change the angular momentum distribution inside the galaxy and disrupt the bar.
There's something, this joins what Françoise was saying, there's something fundamental about the phase-space distribution of baryons that prevents them to form a bar in cosmological simulations.
So I wanted to make a second comment. I'm going to make myself a lot of enemies in the room, but Horizon AGN, it's very nice to know that it's producing galaxies very nicely. But it has one problem, is that it fails to reproduce the segregation of star formation in redshift 0 groups and clusters. So as we found out with Johan and with postdoc Edouard Tollet, who you know well.
Horizon AGN has at least one drawback, is that it's the maximal resolution is about 1 kiloparsec, right? So you do resolve the thickness of disk at redshift 2. But below redshift 1, you don't resolve the thickness of disks. So the response of the disk to tides, interactions, whether this will affect the distribution, the clumpiness of gas, and then the star formation cannot be resolved. So that's why I didn't insist much on the morphology at redshift 0, because you barely resolve them. And star formation at redshift 0, you don't have the resolution to really probe this, I think.
Okay.
We know from galaxy merger experiments that resolving the thickness of the disk is a must to get starbursts in antennae-like galaxies. So clearly, ideally, you would like Horizon AGN with an even better resolution in the IGM and with a resolution of 200 parsec in galaxies.
So it's a miracle that Horizon AGN, Eagle, and Illustrious do fairly well nevertheless.
Very well, or not fairly well? Fairly well. Yeah. The problem is that really resolving the IGM with a sufficient resolution to get virial shocks and resolving the physics of of star formation in galaxies requires the next generation of supercomputers. And you cannot choose the next generation of supercomputers with the numerical codes that we have today, because they will rely on, well, if you want to make them with the usual processors, the x86 processors, you will need one EPR reactor to feed the exascale supercomputers. Or you need a giant windmill farm. I computed it. It's 3 times the surface of Paris covered by windmills to power an exascale computer with standard processors. So it will be different processors. It will be accelerators, GPUs, and so this is a real challenge.
Your figure there shows that even in the case, even Illustris with its very high mass loading factor is still overshooting the observation at low masses.
Yeah.
I wonder, I mean, so does Horizon AGN, but I have not plotted Horizon AGN over Illustris. Does Horizon AGN, since it has lower mass loading factor, go even higher than Illustris at low masses, or not?
Yes. Yes, for both.
Yeah.
They have a factor 3 to 4 above, or a factor 10 above at the low mass. Last question, and we stop after that.
Hi, sorry, I'm not an expert at all of all that, so, but I was wondering, since I think that all simulations right, are very happy when they can show that they are able to reproduce these quantities, like those plots that you show here.
Yeah, yeah.
Actually, they stress this more than other aspects,
yes,
maybe.
yeah.
So, but we see that this means it means something, but it doesn't mean so much, because then you are wrong in some fundamental quantities like the gas fractions and like the feedback and so on. So
you get it about right, but you don't get it correctly.
Yeah, exactly. So my question is, does it really matter, or I mean, to reproduce so well or so pretty well those quantities when then they are fundamental wrong or other fundamental things, or do you think we should add I don't know, observational prediction to be reproduced, or there are other key observational tests to show instead of this one that will be more significant from the physical point of view then?
I wouldn't say that anything is more significant than this, because if you were getting the gas fractions right without this, it doesn't have a better value, because there's a sort of contradiction. You want galaxies that are gas-rich, especially at redshift 2 or redshift 1, that keep high gas fractions for a long time, but you want inefficient star formation. So in some sense, it's easy to get gas-rich galaxies. No feedback, no quenching. You will get gas-rich galaxies. And then at redshift 2, they will be clumpy, because if they are gas-rich, they will be unstable and form giant clumps. The same way, it's easy to lower the efficiency of star formation of galaxies. If you're not enough, you can just boost your IGN feedback. You can boost the stellar feedback by saying, okay, I increase the energy of supernovae, or I add cosmic ray feedback, or whatever you want. You will improve this, but you will lower the gas fraction of your galaxies. So I really think the challenge is to have both together. I don't think one single test can be more valuable than another one. And it's really the tension comes from the fact that you need a lot of gas in your galaxies, but you need to you need to regulate the mass growth of galaxies. It's really the joint thing that is meaningful.
Just a quick comment. You mentioned you focused a lot on the outflow rate and the mass loading factor for the outflow rate, but for the regulation of galaxies, what matters is also the inflow. You mentioned it for the shock heating. You illustrated it for the shock heating. So one solution could be to act also on the inflow rate, not just removing stuff. You could keep this eta equals 1.
Yes.
And okay, you can say, but I still have my problem with the masses of galaxies that would be wrong, except if you manage to act on the inflow rate by quenching the inflow.
That could be another solution. The idea would be to have gas in galaxies that is kept warm or turbulent or something that prevents it from forming stars. Yeah. But basically it means that addressing the low efficiency of star formation and of galaxy growth by expulsive feedback doesn't work because it results in too low gas fraction, incorrect morphologies, etc., etc. So you have to prevent gas from falling into galaxies, to delay the inflow of gas, or you have to let gas fall into galaxies, but just keep it non-star forming by some mechanism, maybe cosmic ray feedback. Could be heating the gas. Maybe. That's a solution, yes. What I've shown is not the only possible solution.
Thank you again.
Thank you.